All right, team, today we're going to talk about 1.8 function composition, and all it is where you take a function and you plug it into another function. So I have this lovely little diagram right here, and taking a look at it, notice you have some input value x. It can remain a variable or it could be a specific number that would be part of the domain of function g, and that gets plugged into this function g. Okay, so whatever that operation is or whatever that rule is, you apply it and your output then would be g of x. Now you're just going to do that again. You're going to take whatever that output is and that's going to become your new input, and that is going to go into function f and do whatever function f says to do, and then your output is going to be f of g of x. So the notation can look one of two ways. So you'll either see it as f of g of x, or you're going to see it written like this. Now, this little notation right here is not an O. This does not say fog x. That actually is f of g of x. And then that little open circle right there is just to indicate that this is going to be function composition. That is our function composition sign. So both notations mean the exact same thing. And I want you to know, just because I'm a little limited, I'm doing these recordings on my iPad right here, and my iPad is not actually reading my math software, so I had to go back in and retype it with just regular formatting. So all of my notation is going to look like this, f of g of x, but no in Connect Math or any kind of quiz or test or anything like that, you could see it looking like this, and it means the exact same thing. Our first approach, just to kind of explore function composition, is going to be to check out a table. So ultimately, we're going to figure out what f of g of 3 is going to be. So in order to do that, you need to determine what this inner piece is going to be. So we always start on the inside most portion of our function composition. So we're going to determine what g of 3 is going to be. So what that tells me is I need to go to function g with an input value of 3, and I need to see where those two values line up. So g of 3 is going to give me 2. So I'm going to use that piece of information because I now know what g of 3 is. So I'm going to substitute in the 2 that we found because that is equal to g of 3. So now this turns into a new problem where we're going to be determining what f of 2 is going to be. So that tells me go to function f, and then go to 2, and then whatever f at 2 is going to be my value. So f of 2 is 8, so that tells me f of g of 3 is equal to 8. Let's try one more like this. So let's try f of 3, and we're going to use that information to ultimately help us determine g of f of 3. So f of 3, that's going to be our inside piece right here, so that's what we're going to find first. So function f, my input value of 3 is 3. So f of 3 is 3. So I could rewrite g of f of 3 as g of 3. That is my equivalent problem because I'm going to plug in 3 for f of 3 because that's what I got from my table. So now reevaluate with function g, add an input value of 3. So it looks like we're going to get 2. So g of f of 3 is equal to g of 3, which is equal to 2. Let's look at this with an actual, we've got a quadratic function for f, and we have a linear function for g. So let's determine what f of g of negative 4 is going to be. So this inside piece is what I'm going to find first. So my scratch work off to the side is going to be to determine what g of negative 4 is. That g right there tells me what function to go to. If that's a g, I'm going to go to function g, and wherever there's an x, I'm going to plug in a negative 4. So g of negative 4 is going to equal negative 4 minus 4, so that's going to equal a negative 8. So I am going to replace g of negative 4 with negative 8. And I'm going to now find f of negative 8. That's my new problem. So function f tells me go up here to this function f. Wherever there's an x value, let's plug in negative 8. And let's see what we get. Don't forget to put the negative 8 in parentheses there because it is being raised to an exponent, and we do need negative 8 times negative 8. So we're going to ultimately end up with a positive 64. and then we have plus a negative 16. So that's going to yield 48. So we would say f of g of negative 4 is equal to 48. We found g evaluated at negative 4, and we got whatever that number is, and then we plugged that number into our function f. Let's try it again, but let's go in the different direction. So let's go ahead and figure out g of f of negative 4. So let's just flip-flop that g and that f. So working on our inside piece right here, f of negative 4 tells me to go to the function f and plug in negative 4. So I'm going to do my scratch work here right up above. And so I'm going to take negative 4 and square it, and then do 2 plus negative 4, and let's clean that up. So 16 plus negative 8 looks like it's going to yield a positive 8. So I could substitute in what f of negative 4 is actually equal to. And f of negative 4 was equal to 8. So I am left with finding g of 8. So g of 8 tells me go to function g over here, and wherever there's an x, I'm going to plug in 8. So 8 minus 4 is 4. So my final answer would be g of f of negative 4 equals positive 4. My next question is, does f of g of negative 4 equal g of f of negative 4? So let's compare these two answers. The f of g of negative 4 yielded 48, and then g of f of negative 4 yielded 4. So 48 definitely is not equal to 4. So this would be an example of something that is not commutative. So we'll say function composition. Okay, it is not commutative. Remember, commutative means that you can change the direction or change the order, and you would still get the same answer. So something that is commutative would be something like addition, because 2 plus 3 is the exact same thing as 3 plus 2. But function composition most definitely is not commutative, because f of g of negative 4 was not equal to g of f of negative 4. All right, let's try it one more time. Same functions as defined before, and sometimes I just want you to know they can look a little bit funky. Like what if we did g of 1? And let's just see how this would work. So off to the side, I would want to find this innermost piece. So I'm going to determine what g of 1 is. So go to my function g and plug in 1. So it looks like g of 1 is equal to negative 3. So that tells me go back, and g of 1 equals negative 3. So that's what's going to get substituted in. So do what's left. It now says g of negative 3. So go back to whatever function it tells you to go back to. And so you're going to have negative 3 minus 4. So g of 1 equals, it looks like a negative 7. Now, just to have some fun here, what if we did g of 1? Notice I could really keep going with these, and it would just be the same process over and over and over again. Well, the kind of cool thing is you already know what this inside piece is, right? Didn't we just determine what g of 1 is, and we found that that was negative 7? So I'm going to go ahead and substitute in negative 7. And now I'm going to see what I'm going to get. So g of negative 7 would be negative 7 minus 4, which equals negative 11. So g of 1 equals negative 11. All right, so let's look at this in terms of just like the functions themselves, and let's keep it with a generic input. Let's keep it with x right here. And so let's determine what f of g of x is going to be and what that's actually would end up looking like. So since I'm not actually plugging in a number, I'm going to do a direct substitution with what g of x is equal to. G of x is defined as x minus 4. So I could rewrite this as f of x minus 4. So that tells me go to my function f, and wherever there's an x, I'm going to replace it with the quantity of x minus 4. So if I have x squared, that means I'm going to have x minus 4 quantity squared. And if I have plus 2x, then that would be 2 times x minus 4. Definitely could do some cleanup work over here, so maybe off to the side, why don't we go ahead and do x minus 4 quantity squared. Remember that means x minus 4 times x minus 4. And we can go ahead and figure this out. So there's an x squared minus 4x minus another 4x, and it looks like plus 16. So clean that guy up. We get x squared minus 8x plus 16. So that's what I'm going to get here. And then I can go ahead and distribute that too. And now I just have some like terms that I need to clean up. X squared looks like a negative 8x, and a positive 2x would be a negative 6x, and plus 8. So this is what f of g of x would be equal to. Now, we're going to be asked a lot about domains on here. So taking a look at what we have for our domain is there's actually going to be no restrictions. So our domain would be from negative infinity to infinity. Because notice, I want to look, when I'm looking for restrictions, I'm going to be looking at whatever restrictions I would have on the inside function. So if I look over here at g of x, that's a linear function and it doesn't have any restrictions. I'm never dividing by 0. I am never going to have a negative number underneath the square root sign. So I don't have any restrictions with my inside function. And then the other place I want to look for restrictions is going to be the new function. So here my new function is x squared minus 6x plus 8, and that's a quadratic function. And quadratics don't have any restrictions either. Their domain is all real numbers. So my domain for my function composition is going to stay all real numbers. Let's look at one that's a little bit different, that will have some restrictions. So let's now define f of x as 3x plus 4, and let's define g of x as 1 over x minus 1. So we're going to determine what f of g of x is going to be, and let's see what we get. So g of x is going to be my inside function, so I'm going to do a direct substitution here. So this is going to be f of 1 over x minus 1, and then that tells me to go to my function f, and wherever there's an x, I'm going to go ahead and plug in that 1 over x minus 1 quantity. So it looks like it's getting plugged in one spot. We have some fraction multiplication here. If you want to make the 3 look like a fraction, that's 3 over 1. And then you can multiply your numerators together. So 3 over x minus 1 plus 4 is one way that you could write it. If you wanted to, you could extend this a little bit further and get a common denominator over here. So x minus 1 would be our common denominator. So both top and bottom would get multiplied by that x minus 1 quantity. And so we would end up with 3 over x minus 1 plus, it looks like 4x minus 4, if I distribute that 4 over x minus 1. And now I can just do some cleanup. So 4x minus 1 all over x minus 1 is another way that I could write this function. Okay, so it could look like this, or it could look like this step right here. Now, when I'm determining my domain, I am looking at restrictions on the inside function. So my inside function here is g, so I'm going to come up here to g, and I need to identify what's going to cause a problem in the domain here. Well, this is a rational function, and so I need to determine what is going to make 0 in the denominator. So I notice that if x equals 1, I'm going to have a problem, because 1 is what makes 0 in the denominator. So I'm just going to make notes off to the side. So this is an issue for me, so I know I can't have 1. Now, look at your new function. Here's my new function. So my new function is also rational. And if I look at the denominator, it's actually the exact same denominator, just the way the numbers worked out in this problem. So 1 causes a problem here as well. So those are the 2 places that I'm checking for issues with the domain. So I can't have 1. So I would write my domain as negative infinity to 1 union 1 to infinity. All right, something that's kind of cool, and just another way to kind of think about this, thinking backwards about your function composition, is looking at it in terms of function decomposition. So if I'm going to tell you that h of x is actually a composition of f and g being 2 separate functions, it's kind of fun to figure out, okay, what are some possibilities that we could have for function f and for function g, that when you compose them in this order, f of g of x, it yields the square root of 5x plus 1. So I'll let you kind of think about that for a minute. If you want to pause the video and look at your paper and kind of try to brainstorm, that would be great. If you have no idea what I'm talking about, then just keep watching here. All right, so let's talk about this. If g of x is going to be my inside function right here, I'm going to look at this problem and I kind of want to see like what's on the inside, like what's happening. So what if we defined g of x as 5x plus 1? So if I have that, now look at what's happening. If I were to plug 5x plus 1 into, say, the square root function, then I would be given h of x equal to the square root of 5x plus 1. This is probably the most straightforward example that I could give. Certainly people in the past have tried to, they get a little creative with what this input is going to look like here and what that f of x is going to look like. And so in the end, when it simplifies, you're left with 5x plus 1. That's great if you want to take on the additional challenge, but by all means, keep it simple. All right, I wish this was time appropriate, but being spring semester, here we go. So just kind of a fun little joke here. So how to make a turducken? Well, let your f function be equal to the chicken, g of x is equal to the duck, and then h of x would be the turkey. So what we have over here is the chicken goes inside the duck, which goes inside the turkey. So that's how you make a turducken. So that would tell you that h of g of f of x, notice the second notation down here, that's what's happening. This inside function, the chicken, got plugged into the duck, which got plugged into the turkey. Sorry, I'm not a very good joke teller, especially online. All right, team, I do want to keep up with vocabulary, so you will have Connect Math homework due on Thursday at midnight, and it'll be function composition. So it'll be going through evaluating some function composition problems, looking at some domains, doing a decomposition, and then let's keep up on the vocabulary. So you're going to be looking at one-to-one function all the way to procedure to find an inverse for next Monday's class. Thank you so much, and I will talk to you guys soon.